Hi folks, Mr. Ackerman here. Thanks for watching. The topic of today's video is the sun, and we're going to be working out of the On Science 9 textbook by McGraw-Hill Ryerson. Now, just so you know, the way the textbook does it, they talk about some of the topics that you see printed over here on the screen, but they also talk about how the sun formed and how the solar system formed. I'm going to leave that topic for another video. And so I've broken it into two parts. Let's call this one Part 1, just the sun and its features. So just so you know what everything looks like, Section 8.2 here. The first part, which talks about the formation of the sun and the solar system, we're going to skip that for now. Like I said, that'll be in another video. Where we're going to pick up the topic is sort of in and around here, and then getting into the features of the sun here. So, without further ado, let's move into some of the slides. The specific topics that we're going to talk about is, first of all, the fact that the sun is a star, which means we're going to have to learn what is a star. We're going to talk about some of the sun's features, and by that I mean the regions of the sun and what are sunspots and solar flares. And we'll finish up with the importance of the sun in terms of how it relates to human beings and planet Earth. So moving into things here, first of all, what is a star? Well, some of you obviously have some idea of what a star is, but the reason what you may know to be a star is not necessarily what people always thought they were. Let me explain. Not too long ago, scientists wondered what was going on up in the stars, and it was natural to think, well, maybe it's something burning, like what we call combustion. This is where, for example, wood, which is carbon and various other elements, plus oxygen in the air, combining in a chemical reaction to form carbon dioxide and water and some energy. It was natural to think that stars maybe were a collection of wood or maybe coal that was burning. And so they asked themselves a question, and the question was, for the sun to produce as much energy as it does, and knowing how big it is, could all the coal or wood in there last long enough to give energy to the Earth for the length of time that we know the Earth has been around? And the answer is that if the sun were made of coal or wood, it could only burn at its present rate for a few thousand years before it would burn out. But we know that the Earth and the sun are billions of years old, so scientists soon realized that no, it can't be made of wood or coal, and it can't be combustion, a chemical reaction that's creating all that energy. So what is it? Well, we now know that the sun and all stars are made up of almost all hydrogen. That's the first element on the periodic table. They're made up of something like 90% hydrogen. And then they're made up of about 9% helium, and the remaining 1% is some mixture of most of the other elements that you see on the periodic table. As you may or may not know, these elements often come to us from stars. Some of them are produced in other ways, but that's the topic of another video. Since the sun is made up of mainly hydrogen and helium, let's take a look at those. Now, I think you know from earlier grades that atoms are made up of electrons and protons and sometimes neutrons, which you see in this picture here. The protons have a positive charge, the electrons go around the nucleus, which is where the proton is, and they have a negative charge, and the neutrons have no charge, they're neutral. Well, hydrogen is just a proton, a single proton, with a single electron orbiting around it. And helium is two protons, shown by the two red pluses there, and two neutrons. Now, in a star, what's going on is that groups of hydrogen atoms essentially are coming together. That's what the word fusion means, to fuse, to bring together, and they are forming helium plus a whole lot of energy, a whole lot more energy than you can get by burning something. In other words, by combustion. And it's known that with the amount of hydrogen that there must be in the sun, there's enough fuel for this sun of ours to last for about 10 billion years. It's believed that it's about halfway through its life right now, and so we've got another 5 billion years to go. So don't worry, the sun's not going to burn out anytime soon. Just so that you can appreciate the huge amount of energy that is produced by nuclear fusion, this is the same energy source that powers hydrogen bombs, nuclear bombs like this. And so truly enormous power source that's available in the sun and all stars. So what are some of the regions of the sun? Well, here's a graphic, here's a graphic which I believe was from Wikipedia, and it's kind of a cutaway drawing of the different zones in the sun. Of course, at the core, this is where the fusion is happening and where all the energy is being produced. Now that energy travels outward toward the outer edges of the sun, and these terms here, convective zone and radiative zone, don't worry about them too much. They're not important for what we're going to discuss. The important thing is that when all that energy reaches the outer surface of the sun, this is called the photosphere. This is what you see if you look up at the sun, the outer layer, the photosphere. The energy gets to there, and then it travels out through space in all directions, and of course some of that reaches Earth. Now let's have a look at what the sun really looks like. Of course, you should never look directly at the sun. You could go blind, but there are ways that astronomers can look at the sun with a telescope without going blind, and they can take pictures. They sometimes use satellites. If you do this, you'll find that on the surface are these strange dark spots which are known as sunspots. And these were discovered several hundred years ago. I think Galileo, the famous Italian astronomer and scientist who discovered them, and he wondered what exactly they were. Well, we now know that they are regions on the surface of the sun that are cooler than the surrounding region. That's why they're a little bit darker. Think of the element on the stove in your kitchen. When it's turned off, it's not giving off any light. You could say it's dark. But if you turn it on and it gets really hot, it begins to glow. So we can see that higher temperatures are associated with more brightness. And the sun is pretty bright because it's pretty hot. The photosphere is about 6,000 degrees Celsius. But the surrounding sunspots are only about, I say only, they're only about 4,000 degrees Celsius, and this makes them seem to be darker than the background, which is the whole sun here. And I want to show you a video of what it looks like if you could actually watch these sunspots as they do their thing. So first of all, the first thing you notice is by watching the sunspots, you can see that the sun is actually spinning just like the Earth is. So that's the first interesting thing. It takes about a month to spin. The other thing is that sunspots regularly change. Sometimes they're there, sometimes they're not there, sometimes they just form out of nothing like these ones. So what exactly is going on that's causing these sunspots to form? We'll answer that question in a moment. Another interesting thing that can happen is that the sun can actually have these firestorms on its surface which can spit out huge amounts of charged particles and along with lots of energy, and these can travel off into space and head in any direction, sometimes hitting Earth. Here's a video which kind of shows what's going on. This is also one from NASA here, so let's play this one. Look at that. This is a real video, probably not in real time. Maybe it's sped up or slowed down. You see, here's what Earth would look like on this scale. So the sun is huge. It's about 100 times wider than Earth. You'd have to line up 100 Earths to see it stretch across the width of the sun. And these huge firestorms are bigger than our entire planet. And when they happen, they can send huge amounts of energy toward the Earth. But the question is, what exactly are these things? Well, as it turns out, The sun and the earth have something in common, and if I ask you to think about what this is, you might begin to figure out what they have in common. Of course, you all know this is a compass. It's used for navigating on the surface of the earth, or in an airplane or on a boat. And the reason this thing works is because the needle of the compass is actually a little magnet that can spin around like this, and the earth actually behaves a little bit like a magnet. Maybe some of you have seen this diagram here, which is meant to show the Earth's so-called magnetic field. Now, what's a magnetic field? Well, if you ever in school got to take a magnet like this one and sprinkle little pieces of iron around it, you saw them line up in this sort of pattern. This is called a magnetic field, or the lines of magnetic force. So I'm showing you a magnet's magnetic field, and here I'm showing you the Earth's magnetic field. They're kind of similar, and they kind of go from the south pole of Earth around to the north in all directions. And so if you take a compass, then the compass needle will line up with these lines and help you figure out what direction is north and what is south. And then you can figure out your way around the surface of Earth. Well, this diagram over here is meant to show the sun and its magnetic field. It's kind of the same as Earth's, although it's stronger, that's for sure, and it's bigger. And sometimes this magnetic field can interfere with the energy that is traveling from the core of the sun out toward the surface. And if it does interfere with that energy, it can cause some areas on the surface of the sun to be cooler than the other areas, and you get sunspots. Because the sun's magnetic field is always changing, therefore the sunspots come and go and they change shape, but sometimes the magnetic field lines get really twisted and tangled and they build up a lot of energy, and that's when you get a solar flare, when they release that energy. So when that happens, something very interesting can happen as a result. I'll show you this next video here, which gives you an idea. Here are the magnetic field lines. This is a drawing, of course, or an animation. It's not a real image. You see the magnetic field lines changing. There are some sunspots there. And it's changed in a way that it's actually broken off and taken some of the charged particles from the sun out into space. This could go in any direction, but it's possible that this collection of charged particles will come toward Earth. And when it does, something very neat can happen, which I'm sort of giving you a preview of in these photos here. Some of you know that these are called the northern lights, the aurora borealis. And if we jump ahead to a different time in the video, 3:10, so right about here, you can see in this animation that as those charged particles come to the Earth's magnetic field, the particles and the Earth's magnetic field interact. The Earth's magnetic field diverts those particles down toward the polar regions. And when that happens, if you happen to be near the North Pole up here or the South Pole down there, you will get to see something very special. When these charged particles hit the Earth's atmosphere, they collide with the atoms in the atmosphere and light is produced. And you end up with what's called the northern lights. And this is not too far from what this looks like if you're up in space. I've never been in space, of course, but if you look at the images, movies from the space shuttle, that's what they show you. This is what it looks like down on Earth. I've only seen the northern lights myself 2 or 3 times, and they weren't like this. But if you go way up north, you can see them like this. Literally beautiful colored lights and patterns dancing through the sky with the stars in the background. And if it's a dark night, of course, it's a lot easier to see these. If the moon is out and it's a bright night, it's not as easy to see it. So you need kind of a moonless night, got the stars in the background, looks really amazing. Anyone who's seen them, this is what they say. Anyway, we're going to finish up with the importance of the sun to Earth. I don't think I need to tell you that the sun is our main energy source. Without the sun, there would be very little light here, and there would be very little heat. Some people might say, well, that's not a big deal. Why don't we just burn coal or gas or wood and get our heat and light from there? but I'd ask those people to think for a moment, where do you think the wood, for example, would come from? In this picture here, I'm showing you a forest with some sunlight coming through. The wood from the trees comes from photosynthesis, where plants create, they create their food from sunlight, water, and so on. Well, without the sun, there can be no plant life, and without plant life, there can't be any wood, so forget that idea. Of course, all animals eventually are dependent upon plants. Someone's got to be eating the plants. Even meat eaters depend on animals that have eaten plants. So clearly, without the sun, there couldn't be any life as we know it on Earth. There couldn't be the amount of warmth that we have. You couldn't see a scene like this on the beach. The oceans would be frozen if they even existed. And how all this is all happening is kind of interesting. This diagram here from your textbook kind of explains what happens to the sun's energy as it approaches and then gets absorbed by the planet. So it's a little complicated. I'll take you through it. First thing that can happen is the sun's energy, the light that's coming in, can be reflected back into space, as you see from this set of arrows right here. It can just bounce off. It can bounce off of clouds, for example, in the upper atmosphere. Some of it makes it to the ground and is also reflected back into space. And this, of course, is very likely to happen near the North Pole or the South Pole, where the land is covered in very reflective snow and ice. But a good percentage of the light actually makes it down to the ground and doesn't get reflected, but rather gets absorbed by the surface. Now, that energy that gets absorbed, of course, heats up the ground, and then the ground gives that heat back up into the atmosphere. You get a feel for this if you've ever seen a scene like this, where you're sort of on a hot summer day looking down the road, and it almost looks like water or glassy, even though it's not raining. This, of course, has something to do with all of the heat heating the air that's near the surface here, and that changes the way the light from the sun passes through and into our eyes, and it gives the feeling of, or the sensation of, a mirage, as it's called. It makes it look like there's water even though there isn't. But the point that I'm trying to get at is that the ground gives off that heat back up into the atmosphere. So that's what this arrow is showing over here. And now something interesting happens. Some of the atoms, or rather molecules in our atmosphere, and I'm thinking of water vapor, H2O. I'm thinking of, make sure that, there we go, H2O. I'm thinking also of carbon dioxide, CO2. I'm thinking of methane, CH4. These, make sure that gets written properly there, CH4. These particular molecules are very good at absorbing the radiation that the ground is giving off and then spitting it back out, often back down toward the Earth. And this radiation is kind of trapped in the Earth's atmosphere. And this is what we call the greenhouse effect. It's very similar in its effect to you lying down in your bed at night and pulling the covers over your body. That traps your body heat in and keeps you warm. You don't need like a hot, hot water bottle or something like they used to have in the olden days, or an electric blanket to keep you warm. You just need a good blanket. Well, the Earth's blanket is these so-called greenhouse gases. Without them, the Earth would be a much cooler place, and again, we would probably be locked in an ice age that would never go away, and we wouldn't have life as we know it. The problem these days is that we're putting too much of these gases into the Earth's atmosphere, and as a result, the greenhouse effect, as it's called, is getting a little too intense, and the planet's warming up. And that, of course, is the topic of a future video. But I think at this point, if you look back at what we set out to accomplish in this video, we've done it. We've talked about the sun and the fact that it's a star, and we've gone into what a star is and how it creates its energy. We talked about some of the features of the sun and the different regions and how important that is to Earth. And finally, we talked about the importance of the sun itself and its importance to life on Earth. Hope you enjoyed and learned something, and I'll see you next time. Thanks for watching.